In this video, we'll be solving Leetcode problem 278, first bad version. So the problem states that we are a product manager of a team, and in the current version of a product, we see that there is some problem. It fails quality check. Since this is developed on the previous version, so there might be case the problem is with the problem is started with some of the previous version. And if you are given with n versions, to simplify, they have given with numbers 1 to up to n. We have to find that which was the first version where this problem started. We are also given with an API which returns a bool to us, which is called as is bad version, and it accepts the version and it returns true or false. It returns true if it is bad version, and false if it is good version. So we has to implement a function to get the first bad version, and the challenge here is to we has to minimize the calls to this API is bad version. So that's the simple problem. In the first input, they have given n equal to 5, which means that we are given with 5 versions and the bad version is 4. So don't get confused that we are giving the solution in input itself. So that's because we are specifying 4 as the bad version, so that my this function returns true if I call on any of the version 4 or it or more. That's why we have to specify this bad version in the input also. And whatever we specify in the input, we should get the same output because we have specified the first bad version as an input. So this is for testing purpose only. And here if we have only one input, for first bad version will also be 1. That's why we have specified bad equal to 1. So to explain this better and see how we can approach to this problem, I'll flip my board. Let's take take an example where n is equal to 8, and let's see, my bad version starts from 6. So our versions will be, so instead of calling 1 2 3, just to segregate that it's not actually number, it is some hash of the repository. If you are using git, it has some hash for each version. So let's call it v1, v2, v3, v4, v5, v6, v7 and v8. And I say my bad version started from 6. So from 6, 7 and 8, these are my bad versions. So very simple approach would be to scan this array sequentially. So if we scan this array from the beginning, scanning means I'll pick each version and call is bad version that they have given with v1, then with v2, v3, v4, v5. Similarly, for all the versions that I see, I'll keep on calling this function. So till 1 to 5, it will give me false because these are not bad versions, these are good. For 6, it will give me true. So in this case, 6 will be my answer because I am scanning from the front, and whichever is the first version which gives me true, that's my answer. So very simple approach that we can follow. So let's try this approach. As we saw, approach is very simple. We have to scan this linearly from the beginning and then call is bad version. So we'll loop over n. We'll start from 1 and go till n plus 1 because our version starts from 1 to n. So we'll call is bad version for each and every versions that we see, and then we'll return v. Whichever is the first version encountered, that will be returned, and that's what we want. And it is guaranteed that there would be some bad version, and it will return uh, the, before the loop ends. So let's try this. Take all the examples. I'll submit. Taking a bit long. Time limit exceeded. So you see, this is a big input, and on that we got time limit exceeded. So let's go back. So the range of input that is given is from 1 to 2 raised to power 31. So this is huge. 2 raised to power 31 goes somewhere in billions. So we has to optimize this. So this solution is actually order of n. N is the number of versions that are given to us. That's because we are only scanning over the range of n that is given to us, and for space I don't know. If we consider this takes constant time, then we can say space complexity is order of 1, but time is order of n, and this is not acceptable because the range of inputs that are given to us are very huge. So let's go back and optimize this. So to optimize this, what we can do is we can see this in more detail. So if we clearly see this, uh, we see that these two type of versions, this good part, let me draw it again. 4, 5, 6, 7, 8. So from here we have bad versions. So if we see this, these are divided into two categories. These are good and these are bad. Divided in category, or we can say that these versions are sorted. That's because first we see all the good versions and then we see all the bad versions. So we can see that these are sorted. So to simplify a bit, if we call all the good versions as 0, so we'll see first all zeros, then all ones, or we can take vice versa also, bad version as 0, good one, so that doesn't matter. So the idea is this thing is sorted. So whenever not only in this problem, whenever we have a problem and the data set that is given to us is sorted, a very important approach that we can think of is binary search. So in this case also we can apply binary search in a way, like we'll start from both the ends and we take the mid. So we'll take v1 v2 up to v8. So we'll take two references, left and right, and we'll calculate the mid wherever mid lies. I don't care. I'll pick that version. Let's say it comes out to be v4, and I'll take this version and call it is bad version with v4. What happens? This will give me false. That's because v4 was not my bad version, this was good version. So this was good version, so we has to go to right, because anything to the left will be good, because it has been clearly segregated. First we have all the good version, then we have all the bad version. So it's clear that this part is not useful to us. We know here we have all the good versions, so we move this left pointer to one ahead of the mid, because this was a good version. So left pointer will move to v5. So left pointer will move to v5. Then again we'll do the same thing, binary search. So this is a very standard binary search. At the end, my left will point to the first bad version, and that we can return. So we'll code this and see if it gets accepted or not. So I'll revert this and code the one that's with the binary search. So this is also simple. We'll take left equal to 1 because we have to start from 1, and then right equal to uh, n, because n is the last version. And then we'll loop over left less than equal to right, and we'll calculate mid. This will be left plus right minus left by 2. Then we'll call is bad version on this mid. Now if mid is my bad version, then I has to go to the left hand side. So my right will be equal to mid minus 1, and if my this version is good, I has to go on the right hand side. So I'll update left equal to mid plus 1, and in the end I'll return left. Let me run this. This works. So there are various ways to implement binary search. Someone might do left equal to mid and handle the condition accordingly. So this is how I implement binary search. So there are other ways also with minor modifications, but all are correct. It's just that we should be aware what will be present in our left and how we are controlling the variable. So that should be fine. So I'll submit it. Yeah, this is accepted, and this is faster than 96%, so which is good. And if we talk about complexity of this algorithm, so again, we are doing just the binary search, nothing else. If we take this as constant, so the complexity of binary search is very standard. This is log of n. N is the number of versions that we are given to us, and base of this log is 2. So not only this problem in various algorithms where we see log n complexity, in most of the cases the base is 2. Otherwise we are dealing with, let's say, a ternary tree or some other special data structure. So that's it for this video. See you in the next one. Thank you.